Boa tarde. Meu nome é Branca Viana, eu sou presidente do conselho do Instituto Serra-Pilheira, que é um instituto privado de apoio à ciência aqui no Brasil. E eu estou aqui para apresentar a Ingrid Daubechies, que é física, matemática e professora da Universidade de Duke, nos Estados Unidos. A palestra vai ser em inglês, então quem precisar de tradução pega o fonezinho ali, com as moças ali, mas essa apresentação aqui rapidinho vai ser em português. A Ingrid costuma dizer que sempre que alguém aparece com uma dificuldade, a primeira coisa que ela pensa é como é que a matemática pode ajudar. Ela hoje vai explicar para a gente como a matemática pode ajudar os curadores e historiadores de arte a exporem e a protegerem os tesouros deles. Ela foi a primeira mulher professora do Departamento de Matemática da Universidade de Princeton, nos Estados Unidos. Ela também foi a primeira mulher presidente da União Internacional dos Matemáticos, primeira e única até agora. Ela ajudou a criar o método de compressão de imagem JPEG, sem o qual ninguém aqui estaria fazendo selfie a essa altura. E ela também trabalha com paleontólogos, ajudando eles a estudarem os fósseis que eles encontram. Além desses talentos matemáticos todos que ela também tem grandes habilidades manuais. Ela sabe fazer tricô, ela sabe fazer crochê, ela sabe costurar. E quando ela era mais jovem, ela uma vez construiu um tear do nada, só porque ela estava interessada em entender como funciona a tecelagem. E ela diz que ela gosta de usar metáforas de tricô e de crochê para ensinar conceitos matemáticos para os seus alunos, porque, segundo ela, essas metáforas são muito melhores do que as metáforas de esporte, que são as metáforas que são usadas normalmente. E isso me fez pensar que essa é mais uma vantagem da diversidade na ciência. Quando a gente tem mais diversidade numa ciência, tudo é renovado na ciência, até as metáforas explicativas são renovadas. Então, vamos agora ouvir a Ingrid. É um prazer ter você aqui, uma salva de palmas para ela.
Thank you. The wonderful thing, first of all, I apologize. I can't speak Portuguese. I hope those of you who need it have a translation, little gadget. And the wonderful thing about being introduced in a language you don't understand is that you can't be embarrassed. So. Okay, so I'd like to tell you about 3 different examples in which mathematicians and mathematical concepts helped in a crucial way in an art history or art conservation way. So the very first of these projects is due to Massimo Fornaciari, and he got a big prize for this from the International Council for Industrial and Applied Mathematics some years back. So this is the Eremitani Church in Padua now. This is what it looked like after the Second World War. In the very final stages of the war, it had been bombed by mistake. It had been mistaken for a strategic target. And in the process of that, wonderful frescoes. This is a reconstruction of a chapel in there, and wonderful frescoes by Mantegna and other very famous painters had been completely destroyed. What people still had was high-resolution black and white pictures, which here have been projected back on the walls of a virtual chapel. And they had the very lowest set of frescoes, which were by far in the worst condition, and which had been taken off to restore them because they had some water damage. So that was the only ones that survived because they weren't there. All the rest was reduced to rubble of this nature, many, many, many boxes. And this rubble was conserved from the late 40s for many years. From time to time, art conservators would open the boxes, would try to do something, but then thought it was a hopeless task and closed them up again. But in the 90s, because more and more computational things were possible, they started a big project. So they took all the fragments they had. They, over a period of several years, they cleaned, stabilized them, numbered them, and then they were all digitized. And so here you see an example of a box of such fragments of frescoes, and then the same thing mirrored on the back with its numbers. So these were all digitized. They were put on CD-ROM. You remember the time? Well, most of you don't remember the time of CD-ROM. But, and then they asked for proposals to how shall we deal with this. Now, you have to remember we're at the end of the 90s. This is 20 years ago. Even big computers could do much less than your smartphones now. So it was a real challenge, but Massimo came up with a solution, and I'll explain a little bit about the solution. In fact, for every one of the things I'm going to talk to you about, I'm going to try to give you a glimpse of the mathematics that made things possible. I will not go into any technical detail. But so there was a very large number of fragments, 80,000, that in total covered a surface of maybe 78 square meters. Many of those fragments actually were unicolored, so there was no hope if you had a unicolored yellow thing to know where it was going to be, given that the only information you had was highly detailed black and white pictures. Only about 20% of the fragments they had actually had detail on it, features on it that might help in reconstructing. And the original, the painted area was certainly at least 10 times of the area that they could cover, and that's many more. I mean, something like 50 times the area of fragments they had with features on it. So it's like trying to do an enormous puzzle where you only have a black and white box cover, and you have lost almost all the puzzle pieces. So for each of those fragments, not only was the location unknown of where you had to put it, but also the rotation. With a jigsaw puzzle, usually you know where to put it because the shape tells you, I mean, in what, you know whether it's horizontal or vertical. That you might not know, but you typically know the orientation. Here the orientation was unknown. If you can compute that if every fragment would have taken an hour of computation time, it would have taken 93 years or something like that to do the whole. So they had to have fast computation algorithms to do this. So, well, how do you work computationally with images? Well, you digitize them. What that means is that you take your image and you represent it by very tiny little squares that have one color, or in this case, black and white, one gray level. And if you blow it up enough, then you start seeing in these individual pixels. You all have seen that somewhere, sometimes on screen. And typically, those are digitized in 8 bits. So what that means is that you take a number from 0 for all black to 255 for all white. And all the numbers, the 254 numbers in between, are different levels of gray, going from very dark to very light. So I sometimes say other people might have 50 shades of gray, but in image analysis we have 254. But you might think, well, it's easy then to see where things are. You just look for where those numbers are. Well, it's not so easy because, first of all, you might have shifted them slightly in the digitization, but there's the other problem that you also may have rotated it. And, for instance, here are 2 blocks of numbers that actually correspond to a little rectangle of different gray levels, and then if I took that rectangle and rotated it, you see that the numbers look completely different. So you can compute that, but if you have to start computing a lot, then you're going to spend time on all these fragments, and you have a problem. So the Massimo realized that mathematicians have tools by means of which they can represent information in images in such a way that rotation is easily dealt with. And what he proposed was to use circular harmonics. So these are very special functions, and I've shown here a certain number of them that we can label very nicely, that we can construct people have known those for a long time. And you see that they have very special properties under rotation. It's very easy to see how they behave under rotation. Actually, it's even easier than what I show you here, because if you rotate any of I'm showing you only the real part. If you rotate any of these under a rotation, then you get another complex, so real and imaginary part. And the whole thing is just given by a complex number that we know exactly multiplying the old thing. So we know exactly how to rotate them with great precision and very fast computation. Now, if you have an arbitrary image that lives on a circle, you can decompose it into these circular harmonics. You can decompose anything at all. And here what is shown is successive approximations. So as we go down every row, and then we go to the next row, and then the next row, and so on, I've included more and more terms in order to build up the image that is at the bottom right. So this is just writing this thing as a sum of circular harmonics. And you can do that with any image. And so you can decompose it in circular harmonics. You have to take a little bit of the first one, maybe a little bit more the second, and so on. So you have all these coefficients. And then if you rotate it over an angle, let's say 33 degrees, then we know exactly how each one of these building blocks is rotated over 33 degrees, and we can compute it. It's just a simple exponential in which 33 appears. And so a rotated version over 33 degrees of the original image, we can immediately just rattle off. And so what that means is that if you know that you have a circular image of a certain size, you can have pre-computed on your the box of your puzzle, if you want, a black and white image, what all the circles would have given. You have, or you can compute it on the fly. We can do that fast too. And you can then easily compute with the table of numbers you have just by looking at these rotation numbers. So all that could be done now very fast. And that was the basis to start the Mantegna project. They put in the center of Padua a little computer lab, and you see how old-fashioned the computers were still, these enormous boxes. Like, I mean, some of you may not even have seen televisions that looked like that. But and what happened is that there was this enormous catalog of thousands and thousands of fragments, and volunteers would pick a fragment, would then launch the program and so on, and the program would look at possible matches and would give a table of the 50 best matches. And typically, it was then, and then it would situate those on the screen. So they were all volunteers, students from different schools in the neighborhood who would come and work there, take turns in the Mant lab. And they would pick, here you see, it's mimicked, you see how they pick one thing. They choose an area, they then pick the biggest circle that is possible to take there, and that would then, for that piece, it would be computed all over, and they would then get a table of possible matches. And you see, because there was human intervention, they could then quickly see what was the most likely match. That last step is something that no doubt we could automate today as well, but in many cases, you don't even want to. In fact, the art historians liked that there was a human component where people would look at it and have a human judgment. So pieces were, because there were very few choices that were likely, were identified, and you can see that indeed there were choices that were given and that might give a good number, but that when you looked at it were clearly not right. And in this way, all the pieces were found. So this is one of the frescoes on which, this is actually a picture taken about halfway the project, on which the pieces were placed. So they had made exact printouts on the exact size of the original frescoes, and every time a piece was identified by the Mant Lab, the art historians would put it on, and it always worked. And so over a number of years, the volunteers went through the whole collection. And you see here a couple of examples. In this particular fresco, you see another fragment, yet another fragment. And much more than just placing fragments on the big fresco, you might say, what good is that? But it tells you a lot. I mean, if you see this, of course, you only have a few fragments of the whole. But look, it tells you how the whole leg covering should be painted, in what color. It tells you how the toes were painted and the leg of the soldier. It tells you the color of his staff, the color of the floor. And with this information, art conservators could start reconstructing the whole fresco. Here's another one. And this is actually how you can presently see it in the church. For reasons of not wanting to falsify history, the conservators decided that they would take big swaths of the paintings and fill in what happened there, but show it in more pastel than the real fragments were. And then they would leave other swaths just in black and white, in gray level, so that you would get impression of things. And this was during the construction of this but we can actually do more. I mean, what I'm going to show you here now is a computational in-painting rather than the in-painting by the conservators. So what you can do is you can mathematically model this idea of, I have information about the whole thing, even though I only have a little bit. You can propagate it from the pieces that you know. And we have equations to do that. And you will see here different stages of propagation. I took the fragments and I've spread them a little bit and a little bit more, and here I close up. And that information was what we had in the black and white and the color, just a few fragments of color. And so what is a project on which Massimo is working now is a project in which people would be able to go to the church and see the reconstruction that has been made by the art historians, but on their smartphone would be able to call up a coloration in which you would see it in vivid color. This has too much contrast, but I mean, because it was not a high quality color copy, but and so you would hold it over and you would see the whole thing. So that was the first example I wanted to tell you about, and you saw circular harmonics played an essential role. Without that idea and what Massimo developed around it, it wouldn't have been possible. And the fill-in of the color is also a very nice construction in which he uses beautiful variational principles. Automatic thread counting. This is a painting by Van Gogh, and in fact, this whole project started when Rick Johnson and I were, well, Rick Johnson first, and he drew me in for other projects, worked with the Van Gogh Museum, and he learned from them that they were about to write a catalogue raisonné on Van Gogh, which means a catalogue in which for every work you write everything you know, all the documentation in which the painter described it to friends. Van Gogh wrote a lot of letters to his brother, Theo van Gogh, all the early, all the restoration that has happened to it, and so on, everything that's known. And one thing that art conservators write in such, or art historians write in such a catalogue, is that they characterize the canvas on which the painting is made. Now, that canvas, in many cases, you think, well, you just turn it over and you take a photograph. In many cases, you cannot do that because paintings have been what's called relined. Canvas, actually, what you use in oil painting is something that slowly digests canvas, and so the canvas becomes very brittle. And so many paintings, in order to preserve them, have another canvas mounted on the back of it to give it more structure, And so you can't see the original canvas, and that has glue to it, so you can't take it off. I mean, you're not going to start poking at a corner and pull off the canvas from a Van Gogh. But you can still see the original canvas if you take an X-ray of the painting. And why can't you see canvas? Of course, canvas itself, X-rays see right through it. But what happens is that the canvas is prepared with lead white, and in order to make it less absorbent so that you don't spend too much paint absorbed immediately in your threads. And the lead white, of course, that is very visible lead in X-rays. And because a canvas has up and down structure, you get a little bit more primer in the valleys than on mountains. And that variation in thickness of that lead white layer is what you see. And you already see very clearly canvas here. Here is a blow-up of one little piece of that, and then it's negative on the bottom, in which you see the threads even more clearly. And so you see that you get a very good image of the canvas. So what art historians used to do is look at, art conservators is look at this under a microscope and with a little, so much of an inch next to it, and then they would count. They would say, 8 threads per inch, and in a different place, and so on. And so they would do this in maybe 10 places, and then their eyes glazed over. But when we were working on this, Rick Johnson and I realized that, but Rick Johnson implemented it, that we can do that automatically very, very easily. If I go back here, what happens is that there's a clear periodicity in this, horizontally as well as vertically. And we have tools, which we call the Fourier transform, in which we can analyze periodicity in different directions. And so you will find directions in which you have the period after which you more or less repeat is the smallest. Because of course if you go obliquely on this, it repeats as well, but it repeats after a longer step, while in the direction perpendicular to the threads, it repeats the fastest. So you can do that and find in which directions it repeats the fastest. And that's not always exactly horizontal or vertical. If you see on this painting, you clearly see that the canvas has undulations. You might say, well, why didn't they stretch it straight? The primer is applied at the factory of the canvas. And if the canvas is not completely straight, and they have huge things, so you can't make it completely straight, then you freeze in those variations at that moment. And you can then take that surface and stretch it on your stretcher, but the undulations of the canvas are still going to be there. And so what doing this little patch Fourier analysis, Rick Johnson found a way of visualizing the information he obtained very nicely. So here this is shown. In fact, he had for each of these things, he had 4 pictures. So for the horizontal threads, for instance, you measure how dense they are. Sometimes you have 8.5, or sometimes you have 9, because the weaving is not always as dense. And so in the top picture, that's the variation in density of the horizontal weave that's shown. In the bottom right picture, what is shown is for the vertical threads, but there he looked at how much does the vertical deviate from the true vertical. I have a true vertical in my picture, but the threads might be a little off. And again, that is quantified and then given with a color picture. And first of all, it gave many more measurements than they had before. But like sometimes happens by serendipity, the art conservators realized they had now a tool that was different from anything they had ever before, because you have a kind of fingerprint of the canvas here. And look, here are 2 paintings that they knew were painted very close to each other by Van Gogh, and they have the same fingerprint. And that's because Van Gogh, like many other painters, would buy his canvas in big lots, a big roll, and then cut pieces from it from which he made his individual canvases on which to paint. And so these clearly were from the same roll. And this, for instance, is a way in which we now know that on the roll of fabric, these 6 paintings were situated, because we have for one direction a fingerprint, and for the other direction a fingerprint. And it is very nice to see that. This tool has been used in the meantime to re-attribute paintings for which people had de-attributed them. Van Gogh, about which people had some questions, but also Velázquez, because Velázquez, I mean, all painters bought these big lots, and most master painters, even though they had studios in which students could work, did not share their most expensive fabric, canvas fabric, with their students. So if something is from a roll made of known paintings, even if it is a slightly lesser than the biggest masterpieces, you have an extra element to do attribution. So they were very happy about this, and what was done was implementing a tool that we know well. Okay, so let me get to the third example in which I myself worked, which is a virtual aging and rejuvenating of paintings on panel, which we call the GISI project. And if you want to read much more or see lots more pictures about this than what I'm going to show, you can find it at a website which I forgot to mark. But it's, I just checked on Google. If you look for the words GISI, like it's spelled there, and reunited, and you'll hear why reunited plays a role, then it's the first hit, at least an hour ago it was. So, okay, but let me first give you a digression of how I came in mathematics and image analysis for art conservation and art history. One of the things I work on is mathematical tools for image processing and image analysis. And in the laudatio for David Donahoe, the JPEG 2000 standard was mentioned, the one with ending JPG2, which is not the one that you have typically on your cameras. That's an older standard. And that uses mathematics that I developed, which is called wavelets. So I started about 9 years ago under the inspiration of Rick Johnson, working on images. And the very first project the Van Gogh Museum asked me was whether I could use the tools I had developed and other tools to distinguish style in a painting. Could I read automatically whether this was a different style from that, or originals from copies? Now, to be quite honest, of all the projects I've worked on, it's my least favorite, although it gives me mails from people who believe they have detected somewhere on a flea market a genuine masterpiece, and they say, could I please, and so on. And of course, I want to ignore all of that. But it was a question they had asked, and I think they asked it because they had no clue about what we could possibly give them. But it gives me an opportunity to tell you a little bit about the mathematics. So I'm not going to be technical, but the idea of doing what is called a wavelet decomposition is that you like to look at information locally in the painting, but at different scales. So imagine taking this black and white pictures of a pair of clogs of shoes by Van Gogh and blurring it slightly. Then, I mean, if you make it digital, you get all these numbers. I have a big table of numbers. I have another big table of numbers. In every place, I can make the difference of those two numbers. And so that's what I see here, and you don't see much at all. Let me enhance it a bit. And what you see is that indeed you see very fine detail, which is what you lost when you blurred. And so let's do that on a little piece. So I blur. I can do that again and again. And every time I will have lost something. So I can look at the difference. And here, in order to make the differences even more apparent, I've used false color. But it's really in black and white, except that some numbers are negative. And that's one reason to use color once you start looking at differences of integers. And so you see that in these three differences, which tell you what information you lost successively, there are things in common. I mean, the edge of the clog is something you can recognize everywhere. And so features that you see in all these differences are edges. But there are other things. If I look in this little place and I blow it up, then you see that there was not much at the first difference. Things emerge and disappear again. So what you can do is you can look at images and decide where details live, at how many scales they live, where they emerge and disappear. You can look at that for different directions, and you can use that to make a little kind of statistical synthesis of what's going on, which looks at the style, implicitly contains the style of the painter. And so we did that for a whole lot of paintings by Van Gogh. We did lots of patches of the same painting, and comparing these statistics within the same painting gave us references for this is the kind of variation you can see for patches within one painting. But then we could look at the patches of another painting, and we could look at how much more that collection of patches differed from the patches within a painting. And we can then compute, we can parlay that into some kind of similarity. And once you have all these similarities between all these pairs of paintings, you can try to visualize that. So what we did is we visualized it as best possible in some kind of mobile, and that in three-dimensional mobile. And that is how we then tried to represent that for the art historians. So visualizing the similarity. So I have a movie here. I've been told to make a big sign for the movie, please movie. It's going to come, we hope, there. And you see here in this, and if I finish talking, and if the movie finishes before I finish talking, please repeat it until I tell you to stop, please. So you see this mobile. The ones with blue, red dots are not the ones that were sold. They're the ones that are not by Van Gogh. They were believed at one time to be by Van Gogh, or they're forgeries. Actually, at the very top, one with the red dot is coming to the foreground. That's a forgery that for the 30s that was later unmasked. And you see that, so please play it again, that the red dot things are more towards the outside of the cloud than at the inside. Okay, so we now go back to the slides. So that was the first thing, but what has been really interesting for me is that I've tried to give this talk not just to audiences of mathematicians who usually like it, but I try, and we have workshops that we do in museums and for art historians. I try to talk to people who may have problems that our methods might be useful for. And so whenever I do that, invariably, I get people who suggest to me interesting problems. Well, they're not always tractable and not always as interesting, but this is one that came about because I gave a talk about what I just told you. So this is again Van Gogh. This is a work that was made a big splash about 10 years ago by Joris Dick and Koen Janssen, who are both material scientists, but who, as a result of this work, now work a lot on using the techniques they know for art conservation and art history. So what they had done is they had looked, this is a painting that Van Gogh painted in his Paris period. Actually, it's really this painting, a patch of grass. And, but if you look at it, put it on its side, and you look at the X-ray of that painting, which you see here, and people had done that a long time before, then you see there's something underneath. And people recognize this as probably a portrait of what they call his Nuenen period. Nuenen is a small village in the Netherlands where he lived with his parents prior to going to Paris to join his brother Theo. After in Nuenen, he had decided he was going to be a painter. That was what he wanted to do in his life, and a full-time painter. He painted before, but there he decided that's what he was going to do. And so he made a whole lot of portraits of peasants in this small village. They lived in very dark little houses, they were poor, and he tried to paint with a very dark palette, which had very few colors, but give an impression of color despite the dark palette. And people are interested in this particular painting because he wrote a letter to his brother Theo saying, I'm sending you here from Nuenen to Paris, a painting in which I think I particularly well succeeded in what I'm trying to do, this rendering color with this very dark palette. We have the letter as we have the full correspondence between Vincent and Theo, which is a real treasure for art historians, but we don't have the painting. Now, of course, once Van Gogh went to Paris, he met Impressionists, he changed his style completely. And so it's not unlikely that this painting that he valued as very special before now became not so interesting anymore. And Van Gogh, like many other painters who were not wealthy, reused canvases a lot. About 30% of his canvases, especially the studies, have something else underneath. Because, well, once he had learned from the study what he wanted, he would put another layer of primer and then paint another study on top. So people were interested, because of this letter, in knowing more about this painting than they could see in this X-ray. And what Joris Dick and Koen Janssen realized was that they knew they could use X-ray fluorescence to, little point by little point, actually make an analysis of the fluorescent spectrum of the pigments on the canvas, which would tell them what elements were represented. And since they knew also the formulas for the paints that Van Gogh used, they could then reconstruct what pigments he had used. And so that would give them information on color. So here you have for that painting what they found in arsine, which is a component of vermilion, and you see that it brings out her lips. And then the other one in antimony is a component, was an element in his Naples yellow. And Naples yellow was probably the only very light pigment he had on his palette, so it gives you a good luminance impression. He had no white probably on his palette. So they then, but you also see here, I hope you can see, kind of weird zigzag patterns. And that's because, well, how did they, now they've built portable things to analyze this, but at that time, they took the painting to a source of high energy X-rays, and this was an X-ray machine, a synchrotron, that was used for other purposes, and where they had to hire a number of hours to work on it. Typically, these machines are used for many, many purposes. Some of them are used for medical purposes to make short-lived isotopes for medical exams. So since they were time-sharing with another application, they had the painting on a sled, and of course they were not moving the beam. That beam is just the beam. It gets sent here, or it gets sent to a different thing, or it gets sent, and so on, and you time-share with other things. So they had to paint the painting on a sled that would move it to a new position under the beam. And when the beam went elsewhere to make its short-lived isotopes that were really paying it rent, then the sled had to stop, and it had to start again. And there was a problem in that synchrony, and since the scanning was done in zigzag pattern, that's why you have these artifacts. And in fact, they're all over, and they didn't know exactly where they were, but there was no question of doing the exposure again. I mean, they had to live with the data. So what they did is they analyzed them more or less by hand, a little bit in Photoshop, the worst things. And they did a colorification in red and yellow and so on, and this is what they came up with, and people were very excited. You saw it made the cover of one of the top journals in analytic chemistry. But they asked us, we who knew about image analysis, could we do more? And so yes, we got the data. The first thing we did is we used variational algorithms in order to get rid of that zigzag stuff, and iterative algorithms to readjust things. The variation, total variation of this image is much smaller than of that image, so that's what we used in order to adjust that. And after we had done that, we had all those black clods. Those are places where you had impasto of Van Gogh's stop painting that prevented the X-rays from probing what was underneath. But we can inpaint. Just like you can propagate information like we saw in the frescoes, you can do that here. And in fact, here it's even easier because they're much smaller pieces. So what we did is we used mathematical algorithms for inpainting. Then we used slightly different algorithms for the long stretches that came from the impasto, from the grasses on top. And then we still had a problem at the eye, and we wondered what to do there. And the art conservator said, oh, if we have a problem in the eye, we use what the painter did in the other eye. And we said, oh, well, we can do that. So we did it. And so already, Joris Dick was very happy with this. But then we wanted to color, restitute color. Now, with the colors that he had, actually here you see how detailed and nice this in-painting works, I mean, on a detail. So, color. We didn't have enough information with the colors in their spectra. We didn't have the blues, we didn't have the earths, so we couldn't really reconstruct. But we looked at portraits, other portraits of the Nuenen period, and we looked at, these are some of the two extremes, one with the highest contrast and one with the least contrast. And both of them have been slightly changed shape to give a shape of the same face, a shape as in the one that we want to analyze. If you look at it in chromance, what that means is you take away all the luminance and you just look at a color where between yellow, orange, red, and so on is the color. This is what you get for that picture. And it looks very, very different. But remember, where it's very dark, you can, of course, not reliably decide on what color it truly is. So you shouldn't take the color in those places. So let's take that away. And then you see that, in fact, they're very, very similar. So the similarity between paintings that were so different, but in that period in Van Gogh, allowed us, with the information we had, to infer from what the painting would have been. So this is what we got out. So we went from what you have on the left here to what you have on the right, which made her come much more alive. And so that was something that made us and them very happy. But let me get to the final topic, the rejuvenation of paintings. So this is the thing for which you can find stuff on the web under Gissy and reunited. So you see the word reunited come up here. The Gissy altarpiece is a not very famous and not very spectacular altarpiece that is scattered all over North America. It probably was taken apart from a church in the Marches, which was a little church, and for that church it was quite a spectacular altarpiece at the end of the 19th century, when many churches decommissioned some of their very old art because, well, they had no money to pay for repairs in the roof, for instance, or some churches were decommissioned. In any case, 3 of those panels, so it was a big altarpiece, well, an altarpiece of a certain size, with a central panel, and then 8 smaller panels, 4 on top and 4 below. And 3 of these little pieces ended up in the North Carolina Museum of Art, 1 in Portland, 3 in the Metropolitan Museum, a central one in the Chicago Fine Arts Institute, and it was actually only discovered in the 60s that they were part, by analyzing style and the punch marks, I'll come back to those, that they were part of the same altarpiece. And the conservator who made this study and who observed this looked everywhere for traces of the last one and never found it. I mean, it might still be in a collection or it might have gotten lost at some point. But in any case, he had this hope of bringing them all together and be reunited. The other museums weren't so, and which would have been easier than in many cases, because at least they were all in the US. There were no border crossings, which always makes it harder. But other museums were not so really interested. They said, well, even if you bring them all together, you're missing one. And he mentioned this to me. We were talking about a completely different project, and we were having coffee, and he mentioned this to me. And I remembered that I had worked before, and she has become a very good friend. I mentioned to him Charlotte Caspers. Charlotte Caspers is a wonderful artist in her own right, but she has trained as an art conservator and she's an expert in what she calls art reconstruction. What that means is that when museums are interested in having a very high quality art reproduction of one of their masterpieces, they commission her. They usually ask for educational purposes. And these are such high quality that you have to be a fantastic expert to actually distinguish. She does this with the same techniques and the same pigments and the same type of materials that would have been used by the original artist. So that's why it's reconstruction, not just copying. And so they commissioned her to reconstruct that missing panel. Now, you might think, how do you reconstruct a panel you haven't seen? Of course you can't. I mean, if ever this panel shows up, what she produced will look different from what was there. The idea was to reconstruct something that would not have surprised if it had been part of the whole altarpiece instead of the true panel at that place. And it could be done because the life of the other panels, the other panels told the story of the life of John the Evangelist. Not only the life of John the Evangelist, but exactly as it was described, and the scenes were all very close to each other in the Golden Legend, which was a medieval bestseller. I mean, this was the time that things were still copied by hand, but although for many books we only have fragments from that time, for the Golden Legend we have a zillion. Well, a zillion might be exaggerated, but we have many copies, so there must have been many copies in circulation. It was a life of saints. And so, since that allowed, I guess there were only two scenes that could have been the final scene, and one was much more likely than the other. So they made a composition for that missing panel of the scene. What happens is that the story here what's going on is that a pagan priest is invoked his gods in order to destroy John's church, and it remained standing. And then John prayed to the Lord, and the pagan temple was destroyed. And then the archpriest said, well, oh, that's trickery. I mean, here we have just executed these two criminals. Drink the dregs from the poison cup, and we'll see whether you live. And John drank, and he lived. And then the priest said, well, if you resurrect them on top of that, maybe I'll believe. And so he resurrected them, and then the priest said, okay, I believe now. And he asked to be baptized. And so that baptism is the scene. So what Charlotte did is she made a composition that was entirely in style with the rest. She tried to take stylistic elements as much as possible from the other panels in order to make something in which she was introducing as few of her own ideas as possible. And here you see her paint that. I mean, she painted it over a number of weeks. And on the website that I mentioned, there's actually a documentary of her painting this, which is really nice. And so this is the final panel. And the curators and the conservators were absolutely delighted. It's gorgeous. It has fresh colors. It's gleaming and scintillating, all this gold that was polished, as was the usage then. It's fantastic. And so they were absolutely delighted with having seen this emerge as she painted it. But then they realized, and so here it's fitting in its place, but then they realized, and you already get an inkling from it here, that they had a problem. Because it wasn't going to fit with the other ones. It was so much brighter and nicer and newer and fantastic. Nobody was even going to look at the other ones. And they were the authentic ones. So then I said, this is a motto of mine when I work with people outside mathematics. Mathematics can help. So we could use image analysis and image processing to study the old panels and virtually age the new panel. And I propose we would do that. And then we would print out a version, a high-resolution version of that aged thing, and display it next to the other panels, so that they had a complete reunited thing. The new panel would, in its full glory, be on a separate wall, and they made a whole display next to it of all the materials that were used for painting it. On a third wall, they had a large screen showing the video of how it was made, and which you can find on the website. And then on the fourth wall, well, that's what I'm going to tell you. Because for virtual aging, what we had to do was we had to do several things. We had to find how to remap the new colors to the old versions. Now, the new colors we knew, Charlotte had chosen her pigments after analysis of the old panels. So they knew what pigments, and so she had used those pigments. So we knew that they were the same pigment in its new version and its old version. So we could study how to translate. And you had to do that pigment field by pigment field because they do age differently. We had to put in cracks, but again, we needed to study the craquelure for that. I'll come back to that. And we would have to age the gold leaf work. And we did all that. But I also realized, and so this is how the printout looked. In fact, it did not, here you can see it looks a little lighter, but that's actually an artifact from how it was lighted when this photograph was taken. In practice, they were conservators from other museums. The painting never travels on its own. It always comes with somebody from the owning museum with it. And there were some who said, how did you, did you make a falsification? Come on, how can you do this? I said, no, this is on paper. Look. But you had to look that closely to see that it was not a fake. It was, but once we could do that, we could also reverse the thing, of course. We could do the inverse with the old ones. We could rejuvenate them. We would have to inpaint the cracks. I'll come back to that a little. We would have the correspondence of colors in the reverse way, and we would have to rejuvenate the gold work. But once we did that, we could virtually look at the new paintings. And so on the fourth wall of the exhibit, that's what happened. They put a big screen on which they showed the new painting, the old panel, as it would have looked new. And okay, we need to study and remove cracks. And you might think, well, it's easy. I just open it in Photoshop, I look at what the color is of the crack, and I look at all those pixels. And you will completely not be able to do this. Because first of all, there are other places that have that brown. Second, the cracks look very different from one place to another. The crack here in the green looks very different from the crack in the brown there. And that might be due to chemical differences. That might be due to the fact that this is a color photograph, and that has influenced things. But the only thing we had was a color photograph. We had to work with that. So we had to find another way. But we knew we could do that because we had done it before. So I could so confidently assert that we could do that because I came out of a different project where on a much more famous painting we had worked. This is the Ghent altarpiece, which is one of the glories of the very early Renaissance in Flanders, where it's one of the first paintings in oils. And it's absolutely glorious altarpiece, polyptych. If you close it, then this is what you get. And there is this scene of the Annunciation here. There's behind the picture of Mary, there's a book on a stand, and if you look at that more closely, we're now looking at something that's maybe 7.5 centimeters, 8 centimeters high on the real painting. Then you see these letters. So, of course, this is not a book. This is a painting of a book. But Van Eyck was an incredible perfectionist, and although many art historians believe that he just tried to make it look like a book, some of them said, we believe that he painted real text here, because some letters were really true letters. And the others said, well, he just painted horizontal and vertical lines. And I said, but why can't you tell? And they said, well, first of all, it's written in this very difficult script, this medieval script that's only horizontal and vertical lines. If you show me a book in this script in a museum, I can't read it. But they can. And I said, but you can read this. I said, yes, but the cracks are really making our job so difficult we can't get, I mean, we can't think them away. And indeed, our visual system is very good at some things and not so good at others. And thinking cracks away, for instance, is something we're not good at. And I said, we can do that. Mathematics can help. If I had known how hard it was going to be, I might have not spoken up. Because it turned out it became a significant part of the thesis, PhD thesis, of an electrical engineering student in Brussels. But he did it. And he found techniques by means of which he found he could locate the cracks, and only the cracks, and that's the hard thing. All the crack pixels, very few false positives, very few false negatives. And then once you've done that, you can inpaint. And we had to inpaint not using the fact that these were probably letters, because that would have been cheating. Just inpaint based on the local information. And so when he'd finished, we got the result on the right. It's a detail, and I thought, well, fat lot of good that has done to us. I mean, I can't read this any more than before, but that's, of course, because I can't read this stuff. Paleographers could. Not fluently, but they could identify several groups of words that convinced them this really was a text. And not only that, but they could trace it back to a text by Thomas Aquinas, which does treat of the Annunciation. So they were absolutely delighted. But that's a side story. Let me get back to my main thing. So I knew we could detect cracks. And in fact, in Gissy, it was easier than in the Daubechies. So here on the right, you see that indeed we can find all those cracks. And so we can then inpaint them. And we had a very nice iterative algorithm to do that. So gradually we inpaint, and we don't actually try to get the very bottom out of it. We don't try to wring it out to the last drop, because then we start creating artifacts. I mean, we try the best we do in a scholarly, responsible way. And the Conservators wanted it that way. Here's another, so after we did that, cracks are treated now, we had to think of color remapping. Now, because Charlotte had so much used elements of the other panels, like in this case, the way John holds his robe was borrowed for the 9th panel from the 8th panel, we knew not only the correspondence in color, but also for the gradations in color. So it was easy to study the two and make that color map. And so, well, first of all, the gold is a different thing, so I've taken away the gold here. So what I've done here is I've shown you the 8th panel on the left as it is, but in rejuvenated colors on the right. And here I have the 9th panel on the right as it is, and in aged colors on the left. Now, we had to also put in the cracks, but we had so much studied cracks that we could put in very believable cracks everywhere. And the density of the cracks is different in different places, depending on the pigment, but we did that. And then we added the gold, aged gold, which we also borrowed from other places, and that was what was put in as a print. But to rejuvenate, we had to deal with rejuvenating the gold. And that was a different problem altogether, because a photograph of a flat, gleaming metal surface is a dull thing. If you see the object in reality, the reason you see it's metal is because you move your head a little bit and the reflections change. And that tells your brain this is a gleaming metal surface. If it's a curved object, you have the same thing. But we had a flat thing, and so we wanted people to get an impression of that gleaming, the beautiful object as it really was in reality. And we realized that we could only do that by doing a reconstruction of a 3D object and all the reflections that you get on that. So, moreover, there are also these punch marks in the at that time in Italian paintings. They made first the surface very gleaming, and then they punched in with a little hammer all these marks that then would give reflections. I think I have it. Yeah, you see it here in the Aurelia on the new 9th painting. You see all these reflections around in the halo around the head of Christ that would illuminate the whole thing. And so they now look very bad because there's no way you can start polishing again that gold. It would all flake off. But we wanted to get that impression for these old panels. And so what we did is we found where all the punch marks were. We located them. We gave that punch mark map to a computer scientist who used computer graphics to model and render the reflections, just like rendering is used in Pixar movies and so on. And we then have another movie that was shown in the, so this is what was on the fourth wall of the museum. You have the movie of this beautiful object gleaming as, I mean, it's not perfect. You see, we have lost things where they sawed the planks, and so we don't know what's there. We could try to infer it, and there's a project for that, but it's not here. And so this gave people an impression. This object doesn't exist. It exists only virtually, of the reunited panel, as we believe it is close to what people must have seen in the 14th century when it was new in its church. And I thank you. The movie can keep going. You can have.
A gente só tem tempo para uma pergunta que eu vou fazer. Eu espero que seja uma pergunta que vocês também estejam interessados em saber, que é how is it that you also use this kind of technique to work with the biologists and the paleontologists to study bones and human evolution?
So there we actually use something completely differently. So when you work, I'm an applied mathematician, so I work on applications. I talk with scientists and engineers in many fields, and because I'm curious. I have an incurable curiosity. And when I detect things where I believe mathematical tools might be useful, I try to talk it over with them, and we go through a lot of talking before we start doing things. But it's the problem itself that decides what kind of mathematics you use. The biologists have very finely discretized surfaces, which they get from CT scans of, actually not the bones themselves, but casts of bones, because they're interested in fossils that are not easily lent, but that people will let them take casts of. So they bring the cast home, and so then they have the surface. They don't have the inner structure. And so they have these surfaces, and they have big collections of surfaces. And the way they deal with surfaces and comparing them, biologists always are comparing and trying to quantify similarities, because that's what they can use in their statistical analysis. So I wanted to look at these surfaces and try to find similarities between different surfaces, or dissimilarities, over a large collection, and use the fact that they are all related through evolution. What that means is that there exists really a mapping from one to the other, because it can go back to the ancestor. So what that means is that if you think of the collection of all the teeth as a manifold, and every one of those teeth has one point on the manifold, each point is also a surface. So you have a collection with some structure, and you want to find that structure from individual things that have structure on their own, and you have mappings from one to the other. So you have what mathematicians call a fiber bundle, and you have a connection. And because the connection should be, if you go around in a loop, at least among close species, should be the identity map, you have a flat connection. And using that, we can actually build distances and try to find the structure of that underlying manifold. So it uses for very different mathematics. It's again signal analysis, and we use denoising techniques and so on, but we use differential geometry rather than harmonic analysis. But the idea is always try to understand what they care for, try to model it right mathematically, and then, if you're lucky, a good understanding of that can give results that are useful to them. And then, of course, the sky's the limit, because then they say, oh, if you can do that, let's do this, let's do that, and so on, and you're gone for years.
Sounds fun.
Yes.
Okay, thank you. Thank you very much. Obrigada, gente.